we'll study about frequency response analysis. Before now, we have studied time response analysis. Today we will study frequency response analysis. What is the meaning of frequency response analysis? It means it is the steady state output response when the input is sinusoidal signal. This is a system where the input is sin omega t and output is a sin omega t plus phi. Here some terms we have to study. First one is A. A is the amplitude of the signal. A is the amplitude of the signal. Omega is the angular frequency. Angular frequency. And phi is the phase difference. Here three basic terms. A is the amplitude, omega is the angular frequency, and phi is the phase difference. We know in a complex number there are two parts. Suppose a complex number is z. Z is equal to x plus j into y. Here x is the real part and y is the imaginary part. Similarly, in a transfer function, if I get the transfer function g of j omega is the transfer function, then its value has two parts. One is magnitude part, that is g of j omega magnitude. One is its angle part, that is angle of g of j omega. If I put this complex gain in case of the output signal, so the output complex will be, here is the amplitude, which is the magnitude part, and the magnitude part of the gain is magnitude of j omega, and the angle part is omega t, and also here the angle part is g of j omega angle. So if the complex is given to the transfer function, then what will be the output? So the output C will be A into g of j omega into sine of omega t plus angle of g of j omega. This is the output of a transfer function when the input is sinusoidal and it is denoted to S domain, that is denoted in the complex number. This equation denotes the output of the frequency response analysis. This is the basic output formula when the input is sinusoidal. Next, we will study the frequency response analysis for a second order system. Okay. We know the transfer function, that is equal to output divided by input. The Laplace of the output transformation with respect to the Laplace of the input transformation. Now, the magnitude and the phase of a second order system. Here transfer function T of s is equal to output C of s divided by input R of s. We know the basic structure, as we have already studied in the time response analysis, is that the formula will be omega n square divided by s square plus 2 zeta omega n s plus omega n square. This is the basic structure for the Laplace transformation of the output with respect to input, which is the transfer function for a second order system. For frequency response analysis, what we will do? The first step is we have to do by putting in place of s, that is j omega. Now we will find what is the magnitude and the phase for this second order system. First step is we have to put s is equal to j omega. Step 1, by putting s is equal to j omega, we can get the transfer function t of j omega. Here t of s in place of s, I have to write j omega. So t of j omega is equal to omega n square divided by, in case of s, that is j omega square plus 2 zeta omega n j omega plus omega n square. Now by simplification I will get omega n square divided by minus omega square, because j square is equal to minus 1, so minus 1 into omega square is equal to minus omega square plus j into 2 zeta omega n into omega plus omega n square. For further simplification, I have to do is that is by dividing omega n square in each term. So omega n square will be dividing, in the upper side I will get 1, in the lower side I will get minus omega square divided by omega n square plus j into 2 zeta omega n omega divided by omega n square plus omega n square divided by omega n square. In simplification, I will get this value is equal to 1 divided by here omega by omega n. If I put it as x, let x is equal to omega by omega n. Now I will get it as minus x square plus j into 2 here zeta into omega n square and 1 omega will be cancelled out. So here the value will be omega by omega n, which is value is x. So here it is plus j 2 zeta into x plus here the value will be 1. If I make simplification such that 1 minus x square is the complex real numbers and j 2 zeta x is the complex imaginary part. So by differentiating the real part and imaginary part, I will get 1 divided by 1 minus x square plus j into 2 zeta x, where x is the omega by omega n. Now this is the j of t of j omega. If I put the magnitude and direction part, for magnitude part the value will be magnitude, that is n mod, which is equal to magnitude of t of j omega, which is equal to 1 divided by 1 plus x square is the real part and 2 zeta x is the imaginary part. So the value will be 1 minus x square whole square plus 2 zeta x square whole root over. This is the magnitude of the second derivative. This is the magnitude for the second order system. If I go for the phase angle, then its angle part will be, for angle part, we know the formula of a complex number, that is z is equal to x plus iy. Here the magnitude is equal to z mod is equal to x square plus y square root over, and its angle theta is equal to tan inverse of y by x. Here I have already got the magnitude part. Now I will go for the angle part, which is equal to tan inverse imaginary part divided by real part. So here the angle theta is equal to tan inverse of, in the opposite the value is equal to 1. So 1 is equal to 1 plus j into 0, which is equal to tan inverse 0. Tan inverse 0 minus tan inverse of imaginary part is 2 zeta x. 2 zeta x divided by 1 minus x square. If tan inverse 0 is equal to 0, so the theta value will be minus of tan inverse of 2 zeta x divided by 1 minus x square. This is the magnitude and the phase angle for a second order system. Next we will study the frequency response analysis, 3 basic terms. The first term is resonant peak. Resonant peak means the maximum value of the magnitude in a transfer function is known as resonant peak. That means we have studied what is the amplitude. The amplitude, the maximum value of a signal. Similarly, the maximum value of a sinusoidal signal in case of frequency response analysis is known as resonant peak. And if the transfer function is given, from that the formula to getting the resonant peak is that 1 divided by 2 zeta into root over of 1 minus zeta square root over. By this formula we can get the resonant peak of a frequency response analysis. Next point is resonant frequency. We have studied resonant peak. At the time of resonant peak, what frequency is occur, that frequency is known as resonant frequency. That means this is the frequency at which the signal is at the maximum point is known as resonant frequency. And the formula for the resonant frequency is that omega r is equal to omega n into root over of 1 minus 2 zeta square root over. This is the formula for getting the resonant frequency. And the last point is bandwidth. Bandwidth means it is the range of frequency. Bandwidth means it is the range of frequency at which the signal is varies from 100% to 70.7% of the maximum value is known as bandwidth of the signal. These are the 3 main terms related to frequency response analysis. Next we will study some techniques which are related to frequency response analysis. In frequency response analysis, mainly there are the four techniques. The first technique is Boad plot technique. Second one is Bolar plot technique. Third one is Nequest plot. In the fourth and the last point is Nichol chart criteria. By this 4 point, we will study all the stability criteria for a frequency response analysis in the next class onwards. Thank you.